As our last comment on electrophilic aromatic substitution, I presented this as being a nice clean reaction generally. So for example, you take benzene, you stew it up with Cl2 and FeCl3, then you make chlorobenzene. But of course, once you've made chlorobenzene, you can still have those Cl2 molecules in there, you've still got the catalyst in there. So there's absolutely no reason why you shouldn't have that chlorobenzene do another reaction to give you 1,2-dichlorobenzene. And you can also make at the same time some 1,4-dichlorobenzene. And if you're really not careful, you might end up making 1,2,3,5-tetrachlorobenzene. Same idea when you nitrate. I've presented it as just here's benzene, here's our nitric acid, there's our sulfuric acid catalyst. Put it all together, you make a mono-substituted, a mononitrated benzene. But of course, you've still got nitric acid, you've still got sulfuric acid, so you could go ahead and also get some of the 1,3-dinitrobenzene or even some of the 1,3,5-trinitrobenzene. And it's even worse when you're doing Friedel Crafts. So here we've got one alkylation, but you could have the 1,2-dialkylbenzene, the 1,4-dialkylbenzene, or even the 1,2,3,5-tetraalkylbenzenes. Now, 2 points to make here. The first is that as with any reaction where you could get continual reacting going on, you can control things, you can control temperature. For example, the nitration reaction is a nice exothermic reaction. So if you do it nice and cool, then you're going to be tilting the reaction in the way you want to tilt it. You control the amount of reagents that you use. So for example, if you have an excess of the benzene and not as much of the other species, then a secondary chlorine, for example, is much more likely to find an unsubstituted benzene than it is to find a substituted benzene. And then you can also remove the products when they're formed in some way or other. So as soon as you've got one chlorine group on, you remove the chlorobenzene before it can react further. Now, some of you will have noticed that I was very careful in my predicted products. I said the chlorine and the alkyl group, you could make the 1,2, the 1,4, or the 1,2,3,5, whereas for the nitro, you either made the 1,3 or the 1,3,5. And that's the major point of the extension material for this topic, so-called reactivity of substituted benzenes. Once you've got a group on a benzene, whether it's a methyl group for toluene, whether it's chlorine for chlorobenzene, whether it's an OH for phenol, well then how those react depends very much on the identity of that substituent. And so we will talk about this from two perspectives. We'll talk about whether having an extra group on the benzene activates or deactivates the benzene ring. In other words, makes it more or less reactive. And then we'll also talk about which positions are most likely to be reacted in. We can have the 2,4 positions, or what I like to call orthopara, or we can have the 3,5 positions that I like to call the meta positions. So that's the extension material, taking the mechanism approach a little bit further to first of all talk about where that Wieland intermediate comes from for regular old benzene, and then talk about the reactivity of substituted benzenes. I hope to see you there.